So good afternoon, guys. This week's tutorial we'll be looking at your assignment, going over the different types of analysis. There's a lot to cover, so if you have any specific questions or any sections of the assignment or the calculation report that you're not sure how to do, please let me know now so that I can focus my attentions on that in this tutorial session. This session will be driven by you guys, so if you have lots of questions, then we will take the full hour. If you don't have any questions about any of the analysis, then I will just do a very brief pass and that'll be it. Okay, so do you have any specific regions or parts of the assignment that you're not sure how to do? Anybody there? Or is everybody just logged on and put it on mute and gone and done something else? Okay, Shristi, so do you have any specific area where you are stuck with, or have you finished the assignment? Okay, still working. That's fine. You've gotten to week 14 to finish it. So I'll just start with a very brief background and cover the theory behind the assignment first before we jump into the actual assignment questions. So I have 3 questions for you guys. Firstly, what are the types of forces that we can come across? All right, so we're designing a coupling, a flange coupling that has to be able to transmit power and torque from one shaft to another shaft. And in the process, it will undergo some kinds of forces. So what are the types of forces that we can expect to experience? So there are lots of different types of forces, but the main ones that we'll be focusing on are the shear forces, tensile forces, and compressive forces. Okay, tensile and compressive forces are examples of normal forces, meaning that they act perpendicular to the stressed surface. So if we look at an example of a round specimen, this is the stressed surface. Tensile force acts perpendicular to that surface, so at 90 degrees to that surface. Tensile tends to pull the object, compressive tends to push the object, so the force goes into the surface, and shear is parallel to the surface, causes a slicing action. So these are generally the 3 types of forces that we will come across in this assignment. There's also other forces like friction, but in this case, we don't have any moving parts or parts that have to slide across each other. So we don't really worry about friction too much. So shear, tensile, and compressive forces are what we're going to look at. Second question. How do we tell if our design is adequate? How do we know that our design is good enough? How do we know that it'll be able to function properly when put in place? How do we know it won't break? So as an engineer and as a design engineer, you have to keep two things in mind, right? You have to keep safety in mind, and you also have to keep cost in mind, all right? Safety is for the public or for the customer or the client. Make sure that your product is safe. Cost is you have to make sure that you're able to deliver the part cost effectively. That's why for a lot of your projects, I've recommended that you include a cost aspect to your design criteria, because cost is one of the major things that people look at when they look at new designs. All right, so this assignment and most of your work that you will experience as an engineer through the years will be based on trying to find that sweet balance between safety and cost, right? In most cases, if you try and make something very safe, you end up making it quite expensive. And if you try and make something cheap, you generally compromise the safety. So just try and get that nice balance between the two. And how do we tell? We use something, or we could look at an example of the stress strain curve. Well, this stress strain curve has been discussed in detail in your lectures, but for you mechanical and civil students, this is pretty much your foundation be using through your years and studies. So the stress strain curve shows the relationship a material has when there is a stress and a strain. So as you increase a force, so let's look at our specimen again. As you apply a force, it'll begin to experience some kind of stress. And proportional to that, you'll also experience a strain, which is the change in length or the change in shape. And this is a directly proportional relationship, meaning as you increase the stress, your strain will also increase. And this is true up until a certain point. This point is called the yield stress. And if you continue to apply more force and the stress continues to go higher than the yield stress, you start to pass into a region called the plastic region. So all the stress values from 0 to the yield stress are called within a region called the elastic strain region, meaning as soon as you release the force, the part will go back to its original shape. As soon as you go beyond the elastic region, you pass into a region called the plastic region. And in the plastic region, you have permanent deformation, which means the part, even when you release the force, it will not go back to its original shape. And this is generally termed as a failure, because nobody wants to design a part or manufacture a part that will change its shape throughout its working lifetime. So we always try and design our parts to have a working stress less than the yield stress. That is how we tell if our design is adequate, if the working stresses are less than the yield stress of the material. So lastly, what is the factor of safety? Factor of safety is a relationship between the yield stress and that working stress. Is the ratio of yield stress and working stress. Now let's say, for example, we have a factor of safety of 1. That means our yield stress is equal to our working stress. And just logically, does that make sense? Would you want to have a yield stress equal to your working stress? Would you trust your life in a part that has a working stress equal to the material's maximum stress that it can take? would you trust a part that has a working stress equal to its yield stress? So the answer is no. Okay. No, you wouldn't trust a part that has a factor of safety of 1. Why? Because that means that we have no margin for error. There is no there's no room for error. Say, for example, in the case of our assignment, say our shaft suddenly experiences a surge in power. It starts producing more than 75 kilowatts. Say it goes to 78 kilowatts. That means there's going to be more torque, more force, and our part will fail. So we always try and account a little bit for maybe unknown forces or unexpected occurrences, which might increase the force. So generally, we can have a factor of safety of 1.2, 1.5, 1.8, can go up to 10, can go up to 100. You know, there's so many different types of factors of safety, and they all depend on the application, and they all should be greater than 1. So then you might ask yourself, why not just design everything to a factor of safety of 10 or 100? Why not just make sure that everything is safe? The reason for that is it comes back to this question, safety versus cost. To make something very safe like that, to make something a factor of safety of 10, means you usually have to make it out of very thick material or use lots of material, or maybe use very expensive materials or very expensive manufacturing processes. So to make something that safe, you compromise the cost. So you have to try again, find that sweet spot. And that all depends on the application of the part, as well as the materials that you're using to produce that part. So if you have very reliable materials and you know with some degree of certainty the types of forces you'll be dealing with, then you use a lower factor of safety, say a 1.2. But if there are a lot of unknowns or there are a lot of people's lives at risk, say in the case of an airplane, you might use a higher factor of safety, say a factor of safety of 10, or a bridge factor of safety of 3. You know, there's lots of different options, and it varies case by case basis. These factors of safety are usually industry standards, and in the case of this assignment, you're given a table with a bunch of factors of safety, and you will use those somewhere in your project to help you determine certain dimensions that you're going to use. All right, so is there any particular area in the assignment that you're having issues with? Something that you're not quite sure how to do? You have 5 different analysis types. You have the torque analysis, key analysis, hub analysis, web analysis, and then the bolt analysis. And the order that you do them in is dependent on the load path. So we have our part A here, shaft A and shaft B. Shaft A is rotating with some torque to transmit some power, and we have to get that same torque and same power, shaft B. All right. Now, the direction of the load, or the path of the load, will go from the center of the shaft, through the shaft to the key, from the key to the hub, from the hub to the flange or the web, from the web to the bolt, and then out the other side all the way to the center of the shaft B. So you should have a shaft analysis, key analysis, hub analysis, flange analysis or web analysis, and bolt analysis. But in this case of the assignment, we are already given the shaft size, so we don't have to worry too much about the shaft analysis. We don't have to do a shaft analysis. We just start with the key analysis, hub analysis, web analysis, and bolt analysis. Each one of these analysis steps, we are trying to find a certain dimension. We are trying to size our part. So for the key analysis, we are trying to find the length of the key. For the hub analysis, we're trying to find the hub thickness above the key as well as the hub diameter. Web analysis, we're trying to find the thickness of the web. And the bolt analysis, we're trying to find either the number of bolts or the size of the bolts. But the first thing we have to do is first calculate for our torque. And torque we can calculate using the information given to us in our design brief. So we're given the power, and we're also given the revolutions per second. And using those, we calculate our torque. Using the formula, power is equal to 2 pi nt over 60, where power is in watts, torque is in Newton meters, and N is in revolutions per minute. Okay. So again, this tutorial session is driven by you guys. So if you don't have any questions, then I will assume that you guys know everything that's going on in this assignment here. So is there any particular place or area where you're a bit stuck, not quite sure how to do something? Okay, so I'll just talk briefly on the. Okay, we will not convert 25 revolutions per second to revolutions per minute. You can convert that to revolutions per minute. Of course, you have to work with revolutions per minute. We are given 25 revolutions per second, so RPS. And you can convert that to revolutions per minute by multiplying by 60. So you come out with 1,500 RPM. Yes. Or similar thing, you could just substitute that into the formula. And notice that 60 and 60 would cancel each other out. So your calculation for torque would be power divided by 2 pi 25. But yes, you can convert it first to RPM and then substitute it back into the formula. That'll also give you the same answer. So I'll just talk a little bit about the hub analysis. So the aim of hub analysis is to try and find the hub thickness, which is this thickness. All right. So the first step you need to do is try and find the force that you're applying. Force can be calculated using the formula for torque. So torque is equal to force multiplied by the distance. The torque is constant. Torque we find in our torque analysis. So force will be equal to the torque divided by the distance. The distance is from the center of the shaft to the center of the surface, which is where we're assuming the forces are going to be acting. The force in this case is acting out of the surface. So it's perpendicular to this red surface here, meaning we're looking at a tensile force. And the distance will be obviously half the shaft diameter, so the shaft radius, plus half of the key height, which is protruding from the top of the shaft, to half of the hub thickness. And that distance, the half of the hub thickness, is an assumed distance by you guys. So this D is equal to shaft radius plus key height divided by 2 plus hub thickness divided by 2. So you can assume any hub thickness at this point, okay? So let's just say we assume hub thickness to be 18 millimeters for now, right? Using that, we would then calculate our tensile force. Since we're looking at tensile force, we'll look at tensile stress. Stress is equal to force upon area. The area is the area of this red zone. All right. The stress we will take from our data given to us in the assignment question. So the assignment says the tensile strength of cast iron. Since we're looking at the hub is made of cast iron. So the tensile stress is 8 megapascals. So we substitute this in K in place of tensile stress. So 8 megapascals is equal to whatever your force value is divided by the area. The area is your hub thickness multiplied by your length of key. Key length is this length, which you found from your key analysis in the previous step. Now, once you've done that, you will try and solve for your actual hub thickness. And this is an iterative process. So you'll keep doing this calculation and keep changing the assumed hub thickness until you get an ideal thickness. So what I mean by that is I'll show you what I've done using an Excel sheet. So Excel is one of the most powerful tools that an engineer can use. And if you can learn how to use Excel effectively and use the functions of Excel, it'll be a great help to you. You can do lots of complex calculations very quickly. So in this case, we have to enter the torque. So the torque is the torque that we calculate in our torque analysis. This is an assumed thickness. So you enter any assumed thickness that you want. It'll calculate the force for us. We give it the tensile strength of the material. So this is 8 megapascals. And it will calculate the ideal hub thickness and then the factor of safety. All right. So like I said, we assume the hub thickness of 18 millimeters or 0.018 meters. We hit enter and it lets us know that the hub thickness should be around 28 millimeters and has a factor of safety of 0.6 if we use a thickness of 18 millimeters. So that factor of safety is less than 1. So that lets us know that we need to make our assumed thickness higher than 18. So let's enter a value of 0.24, 24 millimeters. We see that our hub thickness comes down to 26.8 millimeters, and our factor of safety is almost at 0.9. So we're getting closer to 1. So we still have to increase the thickness a little bit to get to a factor of safety of at least 1. Let's go 0.026. Now you notice that our factor of safety is almost 1. which means the minimum thickness that our hub can have is 26 millimeters. That is the minimum thickness that we can have. So to get a factor of safety of greater than 1, our hub thickness has to be greater than 26. And that is where you come up, that's where you start to ask yourself, okay, what factor of safety should I use? So if you go back to your assignment, you see the different factors of safety. And it says here, factor of safety 1.25 to 1.5 for reliable materials under controllable conditions, which is what we are doing. So we will try and get a factor of safety of anywhere between 1.25 and 1.5. So back to our Excel sheet, we will just keep changing the thickness until we get a factor of safety close to 1.25. If I enter a thickness of 31 millimeters, I get a factor of safety of 1.257, which is an acceptable factor. A factor of safety is just your yield stress divided by your force divided by your assumed thickness multiplied by your length of the key. So yield stress divided by working stress. All right. So the session is about to end. If you could just leave your name and ID numbers in the chat so that I can take your attendance. Do you have any questions? Just leave your name and ID numbers so that I can take your attendance. If you're not part of this session, but you're attending anyways, please also include the tutorial session that you actually belong to, so that it's easier for us to track your attendance. No, for this week's attendance, you don't have to submit anything to the background.